Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. My name is Ainuddin bin Muhammad Rafie. My metric number 2023489684. Code course AS120, Diploma in Science. My lecturer's name is Dr. Siti Nolia binti Ali. Today, I will talk about the topic of isotopes from Chapter 1, Subject Chemistry 131. Now, let's look at the next slide. Now, let's look at the definition of isotope. In chemistry, an isotope is a variant of an element that has the same number of protons and electrons, but a different number of neutrons in its nucleus. This means that isotopes of a given element have the same atomic number but different atomic masses. For example, carbon-12 and carbon-40 are two isotopes of carbon, with 8 and 6 neutrons, respectively. Isotopes can be either stable or radioactive. Stable isotopes do not undergo decay, while radioactive isotopes do. Radioactive isotopes are used in various applications, such as in medicine, for imaging and treatment. Isotopes can be identified and studied using mass spectrometry, a technique that separates isotopes based on their mass-to-charge ratio. This technique is widely used in analytical chemistry and biochemistry. Now, let's look at the background of isotopes. Isotopes are atoms of the same element that have different numbers of neutrons in their nuclei. The term isotope was coined by the British chemist Frederick Soddy in 1930. The discovery of isotopes emerged from two independent lines of research. The first being the study of radioactivity. By 1910, it had become clear that certain processes associated with radioactivity could transform one element into another. Isotopes share similar chemical properties but have different nuclear properties. The existence of isotope was confirmed in stable elements not associated directly with either uranium or thorium with the development of the mass spectrograph by Francis William Aston. Isotope notation. Isotope notation is a written or abbreviated form of an element that reveals its identity, mass number, atomic number, and the number of protons, neutrons, and electrons it contains. Isotope notation is useful for comparing different isotopes of an element, and for nuclear chemistry, isotope notation can be expressed as the name of the element followed by a dash and the mass number, or as the element symbol with the mass number as a superscript and the atomic number as a subscript. The atomic number can sometimes be omitted if it is the same for all isotopes of that element. The number of neutrons can be calculated by subtracting the atomic number from the mass number. For an example, here, helium as the elemental symbol, number 4 as the atomic mass, 2 as the atomic number of proton number. So in here we have three types of element in isotope notation. First, proton, second, electron, and the third one is neutron. So what is proton? A proton is a subatomic particle that has a positive charge of +1 and a mass of about 1 atomic mass unit. Protons are found in the nucleus of the atom, the tiny dense region at the center of the atom, the number of protons in an atom determines the atomic number of an element. In chemistry, a proton can also refer to the hydrogen ion, H+, which is a bare nucleus of a hydrogen atom. The next one is electron. What is electron? An electron is a subatomic particle that carries a negative charge and is found outside the nucleus of an atom. The mass of an electron is approximately 1,837 of the mass of a proton. Electrons are distributed around the nuclei of atoms in atomic orbitals, which can be visualized as regions around the nucleus in which the probability of finding a specific electron is the highest. The properties exhibited by electrons can be studied better with the help of quantum mechanics rather than classical mechanics. The last one we have in here is neutron. A neutron is a neutral subatomic particle that, together with protons, makes up the nucleus of every atom except ordinary hydrogen. The number of neutrons in an atom determines its isotope. Neutrons have a mass slightly greater than that of a proton. So in here we have the reason why isotopes are important in chemistry. First, because they can be used to determine the isotopic signature of element samples via isotope analysis. After that, they can essentially simulate chemical behavior, which is determined by the arrangement of electrons, particularly the outermost electrons. They are, I'm sorry, Furthermore, they are useful in food preservation, archaeological dating of artifacts, and medical diagnosis and treatment. Besides, most elements are found as mixture of several isotopes, and samples enriched in one particular isotope are needed for certain applications in industry, medicine, and science. And lastly, they have the same chemical properties as the element they belong to, but different physical properties. Then, in here we have the use of isotope in medicine. Radioisotopes are isotopes that emit radiation. They are used in medicine for diagnosis, treatment, and research. Some examples of radioisotopes used in medicine are iodine-131. They are used for treating thyroid disorders and cancer. After that, cobalt-60. They are used for external beam radiography. And the last one, technetium-99 M. They are used for imaging the brain, heart, lungs, liver, and each other. So in here, in based on the picture, this is a medical linear accelerator, or as known as LINAC. This is the device most commonly used for external beam radiation treatments for patients with cancer. It delivers high-energy X-ray of electrons to the region of the patient's tumor. So, in this slide, we will talk about nuclear stability. What is nuclear stability? Nuclear stability is the ability of a nucleus to remain unchanged over time. A stable nucleus does not undergo radioactive decay. Radioactive decay means the process by which an unstable atomic nucleus loses energy by radiation. A material containing unstable nuclei is considered radioactive. The decay results in an atom of one type, called the parent nuclide, transforming to an atom of a different type, named the daughter nuclide. Now let's get back to our topic. The stability of a nucleus depends on its binding energy, which is the energy required to break it apart. Higher binding energy means greater stability. The binding energy per nucleon, proton or in I'm sorry, proton or neutron, varies with the atomic number and the neutron to proton ratio of the nucleus. We have noted that the lighter stable nuclei in general have equal numbers of protons and neutrons. For example, nitrogen-40 have 7 protons and 7 neutrons. Heavier stable nuclei, however, have increasingly more neutrons than protons. For example, ion 56 have ion 56 have 30 neutrons and 26 protons. Now we here in the last slide of the presentation. So, in conclusion, isotopes play a crucial role in understanding the diversity and behavior of elements in the realm of chemistry. Their varying atomic masses provide insights into nuclear stability, radiometric dating, and medical applications. As we delve deeper into the microscopic world of isotopes, we unravel the intricate tapestry of elements that shape our understanding of the universe. Thank you for joining me on this journey through the fascinating world of isotopes in chemistry. Before that, before I ending my presentation, let me read you some quotes from Adam Sandler. Chemistry can be a good and bad thing. Chemistry is good when you make love with it. Chemistry is bad when you make crack with it. Thank you for giving your attention from the beginning to the end of this presentation. Thank you and Assalamualaikum.